In this video, we're going to evaluate a definite integral using trig substitution, and I apologize for the smaller font, but it was the only way I could get everything to fit on a slide without going through multiple slides. So hopefully you can zoom in or have really good eyesight. So we're being asked to evaluate the definite integral from root 2 over 3 to 2/3 of dx over x to the 5th times square root of 9x squared minus 1 dx. All right. So, looking at what's under the radical, I got variable squared minus constant. So that tells me I need to use secant in my trig substitution. Again, I need to end up with secant squared minus 1. So I need to put a 1/3 in front of my secant theta so that when I square it, I get a 1/9, and it'll cancel the 9 that's in the front there of that x squared. So we're going to let x equals 1/3 secant theta so that dx is 1/3 secant theta tangent theta d theta. Now, rather than having to go back through and replace all the thetas when I'm done with the x's, I'm going to go ahead and change my limits of integration so that when I get my antiderivative in terms of theta, I can just plug in the endpoints and be done with it. So if x is equal to root 2 over 3, then 1/3 secant theta would be root 2 over 3, or secant theta is equal to root 2. Secant theta is equal to root 2 when theta is pi over 4. If x is equal to 2/3, that gives us secant theta is equal to 2, and that happens exactly when theta is equal to pi over 3. So substituting everything, we get the integral from pi over 4 to pi over 3. dx becomes 1/3 secant theta tangent theta to d theta. We put in 1/3 secant theta in for everywhere we see x, so we get a 1/3 secant theta raised to the 5th power, and a square root of 9 times the quantity 1/3 secant theta squared minus 1. Alright, so we've got a 1/3 on top. When we take the 5th power of the 1/3, we'll get a 1 over 243. We would flip that, invert and multiply. We would have 243 over 3, which gives us 81. So we can pull that 81 out in front. This gives us secant to the 5th. Here, when we square the 1/3, we get a 1/9 times the 9 will give us a 1, so we just end up with secant squared theta minus 1 under the radical. Alright, what cancels? Well, secant squared theta minus 1 is tangent squared. Square root of that is tangent, and you've got 1 on top. So those two pieces cancel. I can cancel one secant with one of the secant on bottom. Leaves us with secant to the 4th on top, on bottom. Moving it to the top, we get cosine to the 4th as our integrand. With cosine to the 4th, that's an even power of cosine, so we're going to need to use our power reducing formula to help us rewrite it. So we replace cosine squared with 1 plus cosine 2 theta over 2 squared. So this is cosine squared squared, and I'm replacing the cosine squared with the appropriate power reducing formula. Squaring the 2 gives us a 4 on bottom, so we can pull that out in front. Multiplying out the top gives us 1 plus 2 cosine 2 theta plus cosine squared 2 theta. The first two terms of that integrand we can integrate easily. The last one we'll need to use power reducing formula again, and remember when we do the power reducing formula, the arcant becomes twice as big. So cosine squared 2 theta becomes 1 plus cosine 4 theta all over 2. And if we do a little housekeeping here, 1 plus a half gives us 3/2, and then we can put the 1/2 in front of the cosine 4 theta. Now we're ready for an antiderivative. Antiderivative for 3/2 is 3/2 theta. Antiderivative for 2 cosine 2 theta is just simply sine 2 theta. Antiderivative for cosine 4 theta is a 1/8 sine 4 theta. And now plug in your endpoints. Pi over 3 for theta. Sine of 2 pi over 3 is root 3 over 2. Sine of 4 pi over 3 is negative root 3 over 2. Put in pi over 4 for theta. Sine of pi over 2 is 1. Sine of pi is 0. So that's where those numbers are coming from. And if we go through and simplify, we get this final answer of 81 over 4 times the quantity pi over 8 plus 7 root 3 over 16 minus 1.